Hello everyone, welcome back to Chemical Engineering and Aspen channel. As you know, these days we are focusing on the module of Chemical Reaction Engineering. So in this regard, we are bringing the lecture number 23 for our valuable viewers. So this lecture is focused on the use of polymath, and we will see how we can use polymath to solve ordinary differential equation. And in this case, we will be solving this example. Already we have solved this example in our previous lectures, and I'm giving its link in the pop-up. But for just a recap, that considers the aqueous phase cis trans isomerization of 2-butene, which we can write it as A goes to B. The reaction is the first order. The volumetric flow rate is constant. Initial concentration is Ca naught. Initial volumetric flow rate is V naught. Final volumetric flow rate is V, which is equal to V naught. The final concentration C of A is equal to zero point 0.1 times Ca naught, and we have to determine the reactor volume V1, which is required to reduce the exiting concentration to 10% of the entering concentration when the volumetric flow rate is 10 cubic decimeter per minute and the specific reaction rate constant is 0.23 per minute. So this is the overall statement of this example. Now just a recap of what we had derived in that part, that we say mole balance for the PFR is dF of A over dV is equal to R of A in terms of species A. And if we talk in terms of B, it will be dFB over dV is equal to R of B. For rate law, minus RA is equal to KCA. Volumetric flow rate is constant, so V is equal to V naught. F of A is C of A into V, and since V is equal to V naught, so accordingly C of A into V naught. Substituting the value of F of A in this differential equation, we get dCA V naught over dV. V naught is a constant term, so that comes out of the differential. Accordingly, V naught dCA over dV is equal to RA. Or we can say dCA over dV is equal to RA over V naught. This is the equation which we'll be using in the polymath. But if we go further to integrate it, that T is equal to V naught over K natural log of Ca naught over Ca. So that was the equation which we had derived in that part, and then we had solved it manually. But in polymath, we will give the differential equation, which is this equation in terms of concentration, and then we will give the required values. Just looking at what was the answer in our that part, that volumetric flow rate was 10 cubic decimeter per minute. The value of K was 0.23 per minute. Ca is equal to 0.1 times of Ca naught. We had substituted the values in that equation. We got volume of the reactor as 100 cubic decimeter or 100 liters. So now we will go to the polymath. We will substitute the values over there, and we will see whether we get the same result or not. So this is the polymath window. We have to first click on new polymath program, and then we get these four equations: nonlinear equations, differential, data regression, and linear equation. So we will be using the differential equation, and we will open it. And we can simply increase its size by pressing control and then scrolling mouse up. Now first we need to enter the differential equation. There is no differential equation, as you can see here. There is no auxiliary equation and no equations entered. And we are using RKF45 method, Range-Kutta method to solve it. Now first we need to enter the differential equation, and we have to click on this dx plus, and accordingly we have to give equation over here. Now our equation is dCA over dV is equal to RA over V naught. So we get CA over V RA over V naught. We have used small a for the species. We can use even capital A, but the nomenclature throughout should remain the same. The initial value of Ca naught is 1 in the system, and if we want to add the comment, we can say the differential for PFR in terms of species A. We have got this equation. Similarly, we have to enter the equation in terms of B, because A goes to B. So the concentration of A will decrease in the system and concentration of B will increase in the system. In the same way, CB RB over V naught, but the initial concentration of B is obviously 0, and we can say differential equation for PFR in terms of species B. Then we have to enter the auxiliary equations, or simply we can say that we have to now check what are the unknown variables which we need to specify. We need to specify rate of reaction, volumetric flow rate, and rate of reaction for species B. So now there are two ways of doing it. Number one is to click Just enter new explicit equation. Like what is the equation? V naught is equal to 10. And we can say cubic decimeter per minute. That equation is entered here, over here. Or if I simply write it, V naught is equal to 10 and just make sure cubic decimeter per minute. So this is one of way to do it as well. So these are the differential equations and their corresponding initial values. And this is the explicit equation. So you can either type it here or you can go to that bars or terms and put over there as well. So simply making sure that all the comments are aligned in the system. Now R of A, we have said minus RA is equal to KCA, but if I enter minus RA is equal to K into CA, it will give me an error, that error in line number 6, which is this line. Please enter a valid implicit explicit equation or boundary condition. So it will take positive value over here. So we have to select RA and we have to say here as minus K into CA, and simply we have set rate of reaction. Then the value of K is 0.23 and the unit was per minute. Then RB, rate of reaction for species B, that is equal to rate of reaction for species A. But we had said RB is equal to minus RA. So these are the previous concepts which we have studied in our previous chapters, or you can say simply the relative rate of concept here. Rate of reaction for species B. Now what is left here? Initial or final values of the independent differential variable not set. What is that? That is the volume. So how we can set it? We have to go here. Initial final values. The initial value is obviously the 0. And the final value, if you remember, we had calculated 100 cubic decimeters. So we will give 100 over here and simply clicking OK over here. Now this complete code is entered, ready for solution. Ticked is here. There are 4 auxiliary equations in the system. There are 2 differential equations in the system. Now there are 3 ways to generate the data. Number 1 is report, graph, and table. Report is by default selected, and if you want to elaborate it in more detail, then you will click on table and then on graph. And this pink arrow, which is solve, is used to provide the answer. So you click on it, and after few seconds, you will get your required result. Now these are the all equations, like these are the differential equations, these are the explicit equations, total number of equations and step size, and all the information is given over here. But now what is our objective? Our objective is to see whether the required concentration is reduced or not. It is reduced from 1 to 0.1002588. So if you click on the calculator, 1 minus 0.1002588 divided by 1 multiplied by 100, so 89.97, which is approximately 90% conversion is achieved, which was our objective in this process. Now you can see the rate of reaction. Initial value was minus 0.23 and then the final value is minus 0.023, which shows that the rate of reaction is decreasing in the system. Don't get confused by the negative sign. This negative sign is for the polymath adjustment, but actually you will see that the value is 0.23 and that it is decreasing to 0.023. The rate of species B is also initially high and then it decreases. Now if you go to this graph, you can see that this blue line represents the A species, while this green line represents the B species. Concentration of species A is decreasing, concentration of species B is decreasing along the volume. And accordingly, you can see the volume, the change in volume, the change in concentration of A, the decrease in concentration of A, the increase in concentration of B, V naught and K are constant in the system. The rate of reaction of A is decreasing and so does B is also decreasing. And you can see at the end, at 100 cubic decimeter volume, you got concentration of A as 0.1 approximately, while that of B is 0.9. So this is the simplest equation, or this is the simplest method demonstrating how to solve ODE using Polymath. Actually, if you remember in our lecture 32, we had said that we have to design a microreactor using this. But before that, we had to solve a simple equation or simple system of solving ODE on Polymath. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video, and subscribe to the channel. Also, click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.